I wanted to start with a couple of announcements about the stuff on the web page. The alert may have noticed that yesterday I had up the Waves 2 problem set. That is now on the website. It was briefly unavailable on Friday afternoon due to some issue in the physics web server, but that problem was sorted by the end of the day. If any of you are having a tutorial in the next couple of days on that material, a bit early, it would be helpful if you told your tutors that the solutions that have been posted on the tutors page were updated yesterday. So if they've got a version dated last week, it's not the latest one. If anybody's looked at the summary of how the material is divided into lectures, you'll have realised it's a complete work of fiction. However, roughly speaking, what's happening is that we did lecture 9 yesterday and lecture 10, most of it, but whereas we hadn't done lecture 8, which I'm going to do today, and then the last bit of lecture lecture 10, which was finished. And then next week I'll do the boundary value problems, although I'll start on them today if I get there. So yesterday I looked at energy transport by the waves and showed that energy was conserved and gave formulae for the energy transport for forwards and backwards going waves. In fact, everything that we've done with regard to waves so far has been based on the D'Alembert solution of a forwards going wave plus a backwards going wave of an arbitrary shape. So this morning I want to discuss an alternative solution to the wave equation based on separation of variables. I believe you covered separation of variables in mathematical methods last term. You perhaps worked through a separation of variables for Laplace's equation, which is a very long job. So the essence, this is a very general technique for finding solutions for a large class of partial differential equations. And not restricted to 2 variables. As I say, you can use it for Laplace's equation in 3 dimensions. So if we start with the wave equation, d2y by dt squared is c squared d2y by dx squared. I'm going to look for solutions in the form of a product. Y is r of x, q of t. And this type of solution is the quintessential standing wave. If we sketch the function r, whatever it might be, then the wave always has that shape. It's just modified at different times by the different values of the function q. So at some other time it might have that shape, and at some third time it might have that shape. So it's always got the same shape in x, but it's modified by the function q of t. And you'll see that the nodes and the maxima and minima are always in the same place. Well, they would have been if I'd drawn it better. So that's a very restricted form of solution, but we'll see that it's in the nature of the method that it enables us to construct arbitrary solutions out of standing waves. So that's the surprising thing, that starting from such a sort of physically dull solution enables us to get solutions that do much more interesting things. So what we do, the method always has the following steps. 1, substitute. 2, I don't know any example that doesn't follow these precise steps. So we substitute the product solution into the differential equation, and we get q of t. Wait a minute, which one did I have on the left? d to dt squared. So I get r of x d2q by dt squared is c squared q of t d2 r by dx squared. Step 2. Divide by the product solution. So in that case we get 1 over q d2q by dt squared is c squared 1 over r d2 r by dx squared. If the equation is separable, you have now separated the variables. So, or you may have to shuffle terms from one side to the other, but the way we had it written down, we'd already separated the variables. That is to say, this side of the equation, so it's now separated. So the variables are now separated. Define separation constant. So the point is, this side of the equation does not depend on x. This side of the equation not depend on t. And they're equal to each other, so they can't depend on either x or t. And in this context, that means that they are a constant. And so we have d2q by dt squared equals, what am I going to call this constant? I'll call it capital K for the moment. Capital K q. And so this equals capital K and d2q, d2r by dx squared equals K over c squared r. So those are our two separated equations. We now have to choose a separation constant. I mean, we have to look at these equations and see what type of solutions they have for different values of the separation constant, and choose a separation constant that does what we want. So we know that quite a lot about the solutions of this equation. If k is greater than 0, we have exponential solutions. If k is equal to 0, we have linear solutions. If it's less than 0, we have oscillatory solutions. The exponential solutions become unboundedly large at large x, necessarily, as indeed does the linear solution. So for this purpose, we will choose k less than 0. That's kind of on physical grounds. You could try the effect of trying a different k. It will satisfy the equation, but whether it's appropriate to the problem in hand depends on the problem in hand. So we'll so we'll put k equals minus omega squared. now that minus sign and the square enforces that that is negative, as we've decided. So that means we have d2q by dt squared is omega squared q, and d2r by dx squared equals k squared r, where k squared is omega squared over c squared, is the usual dispersion relation for the wave equation. Now at this point, so now we have to, so that was step 3. So step 4 is find product solutions and superpose. And I've underlined superpose because the key, the essential part of this process is not that you find a separated solution representing a standard wave, but we get a vast number of separated solutions which because of the linearity of the equation, we can superpose and thereby make solutions of arbitrary complexity. So the final step, the superposition of the product solutions, is absolutely key. Now there is a classic error at this point which is so subtle that it almost never actually causes problems, but is in principle wrong, which is to write down a general solution for this equation and a general solution to that equation and then multiply them together. That is the wrong thing to do, and I'll tell you why in a minute. So the solution to the Q equation is Q is either sine omega t or cos omega t, and the solution for R is either QR is sine kx or cos kx. So the product solution for this separation constant R A sine omega t sine kx, B sine omega t cos kx, C sine cos omega t sine kx, and D cos omega t cos kx. Okay, so Y is any one of those 4 solutions. What would go wrong if you did it the other way around? Suppose you wrote down, so I'll do this in colour because it's wrong. In fact, I'll do it in red because it's wrong. Q is A sine omega t plus B cos omega t, and you wrote down R equals C sine kx plus D cos kx, and then you wrote down Y equals QR equals AC sine omega t sine kx plus AD sine omega t cos kx plus CB. Something's gone wrong. No, cos. Wait a minute. A C A D. So this must be B C cos omega t sine kx plus B D cos omega t cos kx. What's wrong with that? Why is that different from that? Well, I promised it was subtle, and it is. Can't I define AC equals capital A, AD equals capital B, BC equals capital C, and BD equals capital D? The reason is as follows. And once I've written it down, it's kind of obvious. AC multiplied by BD equals AD multiplied by BC. So these four constants are not independent. These four constants are. Okay, that's why it's wrong. It's a very small error, and you need all four constants, all four functions to be in play at the same time for it to matter. If you only had three, it wouldn't matter. This error is very widely dispersed in the literature, and I came across it I've come across it in tutorial notes, in tutorial sheets, and so on. It's the idea that you write down a general solution for the first equation and you multiply it by a general solution for the second equation, and thereby you get a general solution for the product. It sounds very plausible. It just happens not to be true in the most general case. Now, so there is a deeper reason why it's failed, actually, which is that if we go right back to the beginning, here, the function r is not really uniquely, for a given product solution, the function r is not uniquely defined because we could multiply r by some constant, f, and we could divide that by the same constant, f, so we'd have a different function r and a different function q, and we've ended up with the same function y. So constants can be moved between r and q ad lib, and so there's no meaning to the size of r, because you can always modify it by the size of q. So there's no... So if I were to write down, at this point, these constants here have no meaning, because we could scale them up and scale the other ones down, and it would be the same thing. Whereas these constants do have meaning. These multiply. These are elements of the total solution multiplying product solutions. So these scale actual y functions. These constants here do not. The other point I would like to make is that you'll notice that there's a very strong similarity between this approach and what we did at the very outset for normal modes. There's the normal mode solution that we did is essentially separation of variables. We substituted for the normal mode an arbitrary function of t multiplied by an eigenvector. The eigenvector is standing in for the function of x. And the argument uses slightly different words, but it's essentially the same as the argument here about things, one side depending on this and the other side not depending on that, and so on. So the argument there is essentially identical because it's basically a very similar problem. So this here is not the correct approach, but as I say, it very often does not lead to error, because in order to so we now have some kind of general solution which would be of the form y is sigma over I. AI sine omega I t sine omega I sine ki x plus bi sine omega I t cos ki x, etc., etc., all four terms. And with that form of solution, you can do anything. In particular, if you combine, for example, the two terms that I've got, you can write that as in terms of sine omega t minus you can write it of sine in terms of sine omega t minus kx and sine omega t plus kx with different constants. That is to say, those two terms can be combined into a forwards-going travelling wave and a backwards-going travelling wave. And similarly for the other two terms in terms of a cosine. And so you can recover the D'Alembert solution where you're writing the general travelling wave in terms of sines and cosines out of the standing wave solution. So there is an equivalence there. This is often a good way of doing it for particular initial conditions. So the question is, what is the sum over? So that is all values of omega I and ki equals omega I over c, satisfying relevant boundary and initial conditions. Normally, if you've got an unbounded string, this in fact is the sum at all, because k can be more or less anything, so it is in fact an integral, and the functions a, b, c and d are functions of omega. But I'm not going to go down that route, because we're only going to use this type of solution in situations where we have a bounded string. So we're going to apply this to a string fixed at x equals 0 and x equals L. X 0 L. And so if we go back to my where's my general solution gone? Here it is. So the general solutions involve terms involving, that's not very well written, is it? That was a sine in origin. A sine kx and terms involving cos kx. We have a boundary condition at x equals 0, which is y equals 0. And so terms involving cos kx are absent. So perhaps I do need, in fact, to write out all four terms here, because I'm going to use the values of the constants. Plus ci cos omega t sine kx plus di cos omega t cos kx. So we have ci equal di equals 0 in every occurrence of this summation. Okay, so in this case, my solution is now somewhat simpler. It's y is sigma over I sine k. Wait a minute, I've said that wrong, haven't I? Cos kx. No, I need that term. That's the term I don't want. It's b and d. I don't want. So I'll factor out the sine kix and put the other two terms inside a bracket, and they are ai sine omega t plus probably ci cos omega I t. So that is the general solution for a wave. Oh, wait a minute, we haven't used the other boundary condition yet. So we still haven't figured out how to choose the omega i's and ki i's. So the other boundary condition is that y of L is 0 for all time, and That involves sine. If we apply that to each of the separated solutions, then each of the product solutions, then we require sine KIL equals 0, which implies that Ki is I. Actually, I think it'd be helpful at this point to change the index because I don't want to introduce i's on their own. It is n pi over L. So that this argument here is n pi, and sine n pi is 0. So that tells us, so we've actually got this solution here, but we're summing over n, where Kn is n pi over L, and omega n equals Kn over C. And that is my general solution for a wave on a bounded string. And so all we have to do now is to use the initial conditions, the way in which the wave is set up in the first place, to determine the constants A and C. And there are a couple of examples of that on the problem set. Now, if we go back to the problem that we solved using travelling waves a couple of lectures ago, we had a string that was plucked like that. We have to make that triangle function out of sines and cosines. And that's a problem which, by some curious historical anomaly, is not on the first year syllabus, but is on the second year syllabus. So the problem set rather skirts round that. What I intend to do is to approach it from a linear algebra perspective, but since it's off syllabus, I'll defer that for a couple of lectures and do that perhaps in the last lecture. So I'll return to the question of how you find the constants an and cn in general when you have a given initial displacement and initial velocity. But I can make one general remark, however, which is, so at t equals 0, we have y of x 0 equals y of x as usual, and if v is dy by dt, we have v of x 0 equals v of x. So just as in the problem we were looking at yesterday, we have given functions for y of x and v of x. So let's put t equal to 0 and see what happens. So we'll substitute for y of 0, y of x 0. We have y of x is sigma over n. We're going to put t equal to 0. That has the effect that the sine terms go to 0 here, and so we get sigma over n cn sine k n x, and the cosine goes to 1, so that's it. Okay, and knx is explicitly n pi x over L. So that's sort of how we determine the C's, except they're all bound up together in here, and we have to extract them and in some way get an explicit expression for them. And I'll return to how you do that in general, as I say, in a later lecture. And if we just work out what V is, so if we'll differentiate this with respect to T, we get V is sigma over n sine knx. Sine omega t differentiates to omega n an cos omega n t, and cos omega n t differentiates to minus omega n cn cos sine omega n t. And then we'll put t equals 0, so v of x 0 is sigma over n sine knx, and t equals 0, sine omega t goes to 0, we get omega n an, and cos omega n t is 1. So let's just write that in the same form as I wrote the other one. Omega n an sine knx. So that, and Vx0 is equal to this given function, v of x. So that's an equation of essentially the same form as, it's the same problem as this, except that the function y has become the function v, and the constant cn has become the constant omega n an. But if you know how to solve this problem, then you know how to solve that problem as well. So as I say, I'll leave that hanging until next week. And so these different terms in the summation are referred to as modes of the string. And if any of you play stringed instruments, then you may well have practical experience of this. So the first mode, the displacement of the string is half a sine wave. So it's oscillating in that kind of fashion, up and down. Now that's usually that's called the fundamental, and the omega n is kn over c, which is n pi over L c, and n is 1, so omega 1 is that. And so the frequency Fi is 1 over 2Lc, which is the time it would take, travelling at the wave speed, it's the time it takes to go the length of the string and back. It's one round trip. So that's F1. So the next one up is clearly got half the, looks like that, has a node in the middle. I would have thought so, yes. Thank you. Omega over c equals k, yes, of course it is, right. That makes much more sense, right. So that is indeed, so everything that I said was wrong except the symbols were in the wrong place. So yeah, that is indeed the time for a round trip, isn't it? The distance that you travel in time 2L over c is 2L at speed c, which is the round trip. So sorry, thank you, that's very helpful. And if you play a stringed instrument, you can access this by stopping the string very gently in the middle, so that you enforce a node here, and you get this higher frequency, because the frequency now has omega 2 is just 2 omega 1, and F2 is 2f1, which is C over L. And musically, a factor of 2 is an octave. So that takes you up 1 octave musically. And the third one has that kind of shape. And F3 is 3C over 2L. And so relative to that one, we've gone up by a factor of 3 over 2. And musically, that's a fifth. So we've now gone up an octave and a fifth. And then the fourth one is the second octave, and so on. So you go up these harmonics of the waves on a string, quite a lot of them fit into a musical scale. And the first one that doesn't make something that fits somewhere in a musical scale is the seventh one, which is quite a long way up. So similarly, I mentioned that you get very much the same type of equations with acoustic waves. You can achieve much the same effect in a wind instrument, and you can access the same harmonic series by choosing the frequency which you choose the tube to amplify. So you can the same length of tube will access a range of modes broadly similar to those. So those are the modes of the string. And they're looking quite like the normal modes of this very long string mass system, which I was talking about when I was talking about transition to waves. So in fact, they are exactly the same mathematically. They're just a continuum limit of the same of those discrete modes. In the normal modes case, of course, the energy we deduced was a sum over modal energies. Now, it's not a complete surprise that the same is true here. But it's not exactly trivial to show it. So let's set off down that route, and that's probably where we shall get to at the end, by the end of the lecture. So let's have a look at energy in the modal solution. So the ingredients for this are Y is sigma over N well, I'll incorporate the constant into Q. In fact, Rn of x, Qn of t, where Rn is sine n pi x over L, which I shall sometimes write sine knx, and Qn is a sine omega n t plus dn cos omega n t. It's slightly inelegant that the result of what I did over there has left me carrying a D here instead of a B. So let's change that to a B at this point. There. So then, dy by dx is sigma over n drn by dx times qn, and dy by dt is sigma over n rn dqn by dt. So the energy density, U, is dt, dy by dx squared over 2 plus rho over 2 d2y by dt, dy by dt squared. So that's going to require a double summation because we're going to require this summation here squared. So I'll factor out the half, and then I'll have a double summation over m and n. drn dt qn drm by dt qm times the tension large square bracket plus the mass density times r n dqn by dt rm dqn by dt. So that's a fairly lengthy expression, and it doesn't simplify in any meaningful way at this stage. However, if we look at the total energy, which of course, because we've got a fixed length of string, we can do that. Total energy E is the integral from 0 to L u dx. And in that case, then we do indeed get a simplification. So we're going to integrate this from 0 to L. So we've got wait a minute, something's gone horribly wrong. Those should be x's there, shouldn't they? So these are the x derivatives here, and those. So we've got the functions here and their x derivatives here. So that equals 1/2 sigma over m and n t times I m n times qn qm plus rho times j mn dqn by dt dqm by dt, where the integrals are I mn is the integral from 0 to L sine n pi x over L. Wait a minute, this one, no, sorry, that's wrong. This one here is the derivative one, so that will be n pi over L m pi over L cos n pi x over L cos m pi x over L dx, and j mn is the integral from 0 to L times r, which is just sine n pi x over L sine n pi L x over L dx. And these are not particularly difficult integrals, and we will. So what happens is that if we do the cosine one first, so they're all based around those trigonometric sum and difference relations. So there's one that says cos plus cos is 2 cos cos. So that means cos cos there. So this is I mn is n m pi squared over L, integral from 0 to L, 1/2, so it'll be cos n plus m pi x over L plus cos n minus m pi x over L dx. Check. Cos plus cos is cos semi-sum, which is n, cos semi-difference, which is m. Yeah, that's right. And what happens next, of course, is that when you do the integral, the cosine turns into a sine. The sine vanishes at both limits, and therefore the integral is 0, except this second term here depends on n minus m. So when you integrate it, you'll get L over pi with n minus m in the denominator, so the times a sine. Okay, so let's do that explicitly. So I m n is n m pi squared over L squared. The integral from no, wait a minute, I'm going to do the integral, aren't I? So it will be 1/2. So this is from 0 to L. So this will turn into L over pi n plus m sine n plus m x over L, and there'll be an overall minus sign somewhere. Minus sine. Oh no, wait, cos integrates to plus sign, doesn't it? That's wrong. No, this is cos. So here there'll be a factor of L over n minus m pi sine n minus m pi x over L. And when you put in the limits at 0 and L, these signs vanish at both limits, except that you can't do this when n equals m. So this way of doing it is only valid for n not equal to m. If n equals m, I n n is n squared pi squared over L squared 1/2 the integral of. So if you just put n equals m, this step here is correct. N equal to m there, we get cos 2n pi x over L plus 1 dx. So this one is 0. This term integrates to 0 from 0 when you integrate. This term, of course, integrates to L. And so this gives L over 2 times n squared pi squared over L squared. So what happens is that the cross terms in the expansion here involving Qn and Qm vanish. We just get a sum over terms with n equals m here. Exactly the same thing, or not exactly the same thing because it's a different integrand, but an extremely similar thing happens with Jmn, because Jmn is a sine-sine, and that also gives two cosines. And so we actually get a very similar result. But Jmn is 0 for m not equal to n, and Jnn is, now where's the definition? J. Here is sine squared, it's the integral of sine squared, which is just L over 2, isn't it? So again, the cross terms between the different modes cancel, and we're just left with a single summation. So that means that the total energy can indeed be written as a sum over modes. E is sum over modes, and it's just at the top of the board there. 1/2 L over 2, that came from the integral, and then we've got IMN, which is m squared pi squared. Well, actually, I'm going to write that as k squared, if that's all right. I shall write that as k squared qn squared, and that's got a factor of the tension plus the mass density times jmn, and jmn was just L over 2, which I've already got here, times dq by dt squared, and that's n. Right, so if I were to factor out, for example, a rho, I could write that in the form sigma over n, rho over 2, L over 2. So they could in fact come out of the summation altogether. So here we will have T over rho, which is c squared, so I've explicitly written the total energy at any time as a sum over terms relating to each mode n. So I've satisfied the first claim, which is the energy is a sum over modal energies. I'm now going to make a second claim that each of the modal energies is also constant. I haven't got time to do that now, so I will do that at the beginning of next week. Thank you very much.